Welcome to AERO 1020, Theory of Flight, presentation number 6 on Newton's laws. In this presentation, we'll discuss the 4 forces acting on an airplane. We'll talk about Sir Isaac Newton and who he was, and we'll discuss his first, second, and third law of motion. First of all, it's important to remember that there are 4 forces acting on an airplane in flight. Lift opposes weight, and thrust opposes drag. When lift is equal to weight and thrust is equal to drag, the airplane is in straight and level, unaccelerated flight. So before we move on, we need to define a couple of terms. The word force is a quantitative or a numerical description of an interaction between two bodies or between a body and its environment. And we measure force with a couple of different units. We can use the English system and measure a force in pounds, or we can use the metric system and measure a force in newtons. You can imagine this sumo wrestler and this small child, and the force required to move each one of these would be totally different. You would need a greater force in order to move the sumo wrestler than you would to move the child, because they both have different masses. Now the word acceleration means a change in the velocity or a change in the speed of an object over a given amount of time. So who was this Sir Isaac Newton? Isaac Newton was a British physicist who lived in the 1600s. And he didn't start out as a physicist. He was actually a physician by trade, but he liked to dabble in physics and mathematics. And he published a paper known as a Principia in 1686, which describes all motions in accordance with 3 laws. And these 3 laws have been applied to aviation. Newton's first law is known as the law of inertia, and it states that a body at rest tends to remain at rest, and a body in motion tends to stay in motion unless it's acted on by some outside force. We can apply this law to gliders, airplanes, football players, any object that is in motion. And this law assumes the absence of outside forces. So it assumes the absence of gravity, it assumes the absence of friction, and so on and so forth. Here's a link to a video that may help you better understand Newton's first law.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most defensive players in the NFL have a single goal in mind: to get downfield as far and as fast as possible.
We're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's the battle to see who's the toughest.
Defenders, on the other hand, have a different goal: to stand in the way of the offensive player and stop his forward progress.
When you come in and making that tackle, you've got to come in and you've got to stop him right there on the dime.
Who wins this epic battle between the ball carrier and the defender? Newton's first law of motion helps supply some answers.
Newton's first law says that if an object is at rest, it requires an unbalanced force to make it not be at rest. Or similarly, if an object is in motion, it tends to stay in motion in a straight line at a constant velocity unless an unbalanced force acts on it.
In football, we see unbalanced forces whenever one player exerts a force on another and causes him to change his direction and/or speed.
So imagine that a quarterback is just taking the snap from the center, and a lineman gets free from the opposing team and is coming from the other side. And when they collide, you can see an unbalanced force acting on the quarterback, driving him across the field in the direction of the charging lineman. That's about as unbalanced as it gets.
In physics, a player's natural resistance to that unbalanced force is something called inertia.
On the football field, you can think about inertia as being a running back who's already in motion, doesn't want to change the fact that it's already in motion. So it's going to take some external unbalanced force, i.e. a defensive player, to stop that running back.
Consider former New Orleans Saints running back Deuce McAllister, who at 6'1", 231 pounds, used his inertia when running to make him hard to tackle.
The size of the player is important to the concept of inertia because higher mass means more inertia.
But a player's mass is different from his weight. Mass is a measure of how much matter an object has, while weight is a measure of how strongly an object's mass is attracted by gravity.
So for example, a body on Earth would have the same mass as that body on the moon, but it would weigh less on the moon because gravity is less on the moon than it is on Earth.
NFL players with more mass have more inertia and are harder to move off their path. This concept even works on a quarterback sneak, when a quarterback uses the combined mass of his entire offensive line to gain a yard or two.
If you've got an offensive line that can overpower the defensive line, that's just what you do. You get on their hip and you just fall. I mean, you just ride that wave forward.
In the NFL, whenever players go head-to-head, it's Newton's first law of motion that helps determine who will win the battle of the gridiron.
Newton's second law can be stated as the law of force and motion. And we can state this mathematically as a force equals a mass times the acceleration of the mass. And it applies to all objects in motions. We can apply this to airplanes. So remember the first law of motion. An object tends to stay at rest unless it's acted on by some outside force. Here's a link to another video that can help you better understand Newton's second law.
Newton's first law tells us that an object at rest will stay at rest, and an object with a constant velocity will keep having that constant velocity unless it's affected by some type of net force. Or you actually could say an object with constant velocity will stay having a constant velocity unless it's affected by net force, because really this takes into consideration the situation where an object is rest. You could just have a situation where the constant velocity is 0. So Newton's first law, you're going to have your constant velocity. It could be 0. It's going to stay being that constant velocity unless it's affected, unless there's some net force that acts on it. So that leads to the natural question. How does a net force affect the constant velocity, or how does it affect the state of an object? And that's what Newton's second law gives us. So Newton's second law. Second law of motion. Second law of motion. And this one is maybe the most famous. They're all kind of famous. Actually, I won't pick favorites here. But this one gives us the famous formula: force is equal to mass times acceleration. And acceleration is a vector quantity, and force is a vector quantity. And what it tells us, because we're saying, OK, if you apply force, it might change that constant velocity. But how does it change that constant velocity? Well, say I have a brick right here, and it is floating in space. Newton's second law tells us, and it's pretty nice for us that the laws of the universe, or at least in the classical sense before Einstein showed up, the laws in the universe actually dealt with pretty simple mathematics. What it tells us is if you apply a net force, let's say on this side of the object, and we talk about net force because if you apply two forces that cancel out and that have 0 net force, then the object won't change its constant velocity. But if you have a net force applied to one side of this object, then you're going to have a net acceleration going in the same direction. So you're going to have a net acceleration going in that same direction. And what Newton's second law of motion tells us is that acceleration is proportional to the force applied, or the force applied is proportional to that acceleration. And the constant of proportionality, or to figure out what you have to multiply the acceleration by to get the force, or what you have to divide the force by to get the acceleration, is called mass. That is an object's mass. That is an object's mass. And I'll make a whole video on this. You should not confuse mass with weight. And I'll make a whole video on the difference between mass and weight. Mass is a measure of how much stuff there is. Now that we'll see in the future, there are other things that we don't normally consider stuff that does start to have mass. But for our classical, or at least a first-year physics course, you can really just imagine how much stuff there is. Weight, as we'll see in a future video, is how much that stuff is being pulled down by the force of gravity. So weight is a force. Mass is telling you how much stuff there is. And this is really neat that this formula is so simple, because maybe we could have lived in a universe where force is equal to mass squared times acceleration times the square root of acceleration, which would have made all of our math much more complicated. But it's nice. It's just this constant of proportionality right over here. It's just this nice, simple expression. And just to get our feet wet a little bit with computations involving force, mass, and acceleration, let's say that I have a force, and the unit of force is appropriately called the Newton. So let's say I have a force of, I have a force of 10 newtons. And just to be clear, a newton is the same thing. So this is the same thing as 10 kilogram meters per second squared. And that's good that a newton's the same thing as kilogram meters per second squared, because that's exactly what you get on this side of the formula. So let's say I have a force of 10 newtons, and it is acting on a mass. Let's say that the mass is 2 kilograms, and I want to know the acceleration. I want to know the acceleration. And once again in this video, these are vector quantities. If I have a positive value here, we're going to make the assumption that it's going to the right. If I had a negative value, then it would be going to the left. So implicitly, I'm giving you not only the magnitude of the force, but I'm also giving you the direction. I'm saying it is to the right because it is positive. So what would be the acceleration? Well, we just use F equals ma. You have, on the left-hand side, 10. I could write 10 newtons here, or I could write 10 kilogram meters per second squared. And that is going to be equal to the mass, which is 2 kilograms, times the acceleration, And then to solve for the acceleration, you just divide both sides by 2 kilograms. So let's divide the left by 2 kilograms. Let's divide the right by, or let me do it this way. Let's divide the right by 2 kilograms. That cancels out. The 10 and the 2, 10 divided by 2 is, 10 divided by 2 is 5. And then you have kilograms canceling with kilograms. Your left-hand side, you get 5 meters per second squared. And then that's equal to your acceleration. Now, just for fun, what happens if I double? What happens if I double that force? Well, then I have 20 newtons. Well, I'll actually work it out. Then I have 20 kilogram meters per second squared. Kilogram meters per second squared is equal to, I don't have to color code this, 2 kilograms times the acceleration. Divide both sides by 2 kilograms. And what do we get? Cancels out. 20 divided by 2 is 10. Kilograms cancel with kilograms. And so we have the acceleration in this situation is equal to 10 meters per second squared, is equal to the acceleration. So when we doubled the force, we went from 10 newtons to 20 newtons. The acceleration doubled. Went from 5 meters per second squared and to 10 meters per second squared. So we see that they are directly proportional. And the mass is that how proportional they are. And so you can imagine what happens if we double the mass. If we double the mass in, let's say in this situation, with 20 newtons, then we won't be dividing by 2 kilograms anymore. We'll be dividing by 4 kilograms. And so then we'll have 20 divided by 4, which would be 5, and would be meters per second squared. So if you make the mass larger, if you double it, then your acceleration will be half as much. So the larger the mass you have, the more force you need to accelerate it. Or for a given force, the less that it will accelerate it. The harder it is to change its constant velocity.
Now, Newton's third law of motion is known as the law of equal and opposite reaction. And it's used very often in aviation to describe left turning tendencies and also as a partial description of lift. Examples of this law are torque and downwash. Torque describes one of the left turning tendencies of an aircraft because the propeller on an airplane rotates clockwise as it's seen from the pilot station. The airplane wants to roll or rotate counterclockwise. That's known as torque. Downwash is the action of the air flowing over and down off of the wing. That downward motion of air flowing from the wing forces the wing up, contributing to lift. Here's another video link that may help you understand Newton's third law.
We're now ready for Newton's third law of motion, and something, once again, you've probably heard what people talk about. But in this video, I want to make sure that we really understand what Newton is talking about when he says, and this is a translation of the Latin version of it, to every action there is always, and just so you're clear, Newton was English, but he wrote it in Latin because at that point in time, people wrote things in Latin because it was viewed as a more serious language. But anyway, to every action there is always an equal and opposite reaction, or the forces of two bodies on each other are always equal and are directed in opposite directions. So what Newton is saying is that you can't just have a force acting on some object without that object also having an opposite force acting on the thing that's trying to act on it. And just to make it clear, let's say that we have and we'll talk about these examples in a second. Let's say that I have some type of block right over here, and that I move and I press on the block and I try to push it forward. So this is my hand. This is my hand trying to press on the block and exert a force, a net force in that direction, so that the block moves to the right. Maybe this block is sitting on some type of ice so that it can move. So let's say that I have some that doesn't look like ice. Do it in a more ice-like color. So the block is sitting on maybe some ice like that. So Newton's third law saying, look, I can press on this block, and sure, I'll exert a net force on this block, and that net force will accelerate the block, assuming that I can overcome friction. And if it's on ice, I can do that. But that block is going to exert an equal and opposite force on me. An equal and opposite force on me. And for direct evidence, this is something, even though it might not be so intuitive when it's said, this equal and opposite force, but direct evidence that it's exerting an equal and opposite force is that my hand will get compressed. I could actually feel the block exerting pressure on me. Take your hand right now and push it against your desk or whatever you have nearby, and you are clearly exerting a force on the desk. So let me draw. So let's say I have a desk right here. And if I try to push on the desk, so once again, that's my hand right here, pushing on the desk. If I push on the desk, and I'm actually doing it right now while I record this video, you'll see, so I'm clearly exerting a force on the desk. If I do it hard enough, I might even get the desk to shake or tilt a little bit, and I'm actually doing that right now. But at the same time, you'll see that your hand is getting compressed. The palm of your hand is being pressed down. And that's because the desk is exerting an equal and opposite force on you. If it wasn't, you actually wouldn't even feel it, because you wouldn't even feel the pressure. Your hand would be completely uncompressed. Another example of that. Say you're walking in the beach. Say you're walking on the beach, and you have some sand right here. If you were to step on the sand, so let's say that this is your shoe. Do my best attempt to draw a shoe. So this is the shoe. If you were to step on the sand, clearly you are exerting a force on the sand. You are exerting a force on the sand. The force that you're exerting on the sand is the force of your weight, the gravitational attraction between you and the earth. You are exerting that on the sand. The sand is also, and another evidence of that is that the sand is going to be displaced. You're going to create a footprint. The sand is going to move out of the way because it's being pushed down so hard. So clearly you are exerting a force on the sand. But the sand is also exerting an equal and opposite force on you. Is also exerting an equal and opposite force on you. And what's the evidence of that? Well, if you believe Newton's second law, if you have this gravitational force on you, you should be accelerating downwards unless there is some other force that balances it out. And the force that balances it out is the force that the beach or the sand is exerting on you upwards. And so when you net them out, there's a zero net force on you. And that's why you get to stay there, why you don't start accelerating down towards the center of the Earth. Other examples of this, this is maybe the most famous example of Newton's third law, is just how rockets work. When you're in a rocket, either trying to escape the atmosphere or maybe you're in space, there's nothing to push off of, nothing to push off that let you accelerate. So what you do is you keep stuff to push off in your fuel tanks. And when you allow the proper chemical reactions or the proper combustion to take place, what it does is it expels gases at ultra high velocities out the back of your rockets. And each of those particles, you're exerting a force on them, enough force, even though they're super small mass for each of them, they're going at super high velocity, so they're being accelerated tremendously. So there's an equal and opposite force on the rocket, the thing that is actually expelling the gas. And so that's what allows a rocket to accelerate even when there's nothing in this direct vicinity to push off of. It just expels a bunch of things, or it accelerates a bunch of things at a super fast rate. It exerts a force on all these particles, and that allows an equal and opposite force to accelerate the rocket ahead. And another example of this is if you ever find yourself drifting in space, and this is an actual useful example so that you don't end up drifting in space forever. Let's say we don't ever want this to happen. This astronaut, by some chance, he loses his connection to this little tool arm right here on the space shuttle, and he starts drifting away. He starts drifting away. What can that astronaut do to change the direction of his motion so that he drifts back to the space shuttle? Well, you look around, you're like, wow, there's nothing to push off of. He doesn't have any wall to push off of. And let's just assume he doesn't have any rocket jets or anything like that. What could he do? Well, the one thing you could do, and this is the situation if you're ever drifting in space, is you should find the heaviest, or I should say the most massive thing on you, and we'll explain the difference between mass and weight in a future video. But you should find the most massive thing that you can carry, that you can take off of you, that you can throw, and you should throw it in a direction opposite yourself. So let me put it this way. If I throw, let's say I'm in space and I'm floating. I'll make it look like the glove of a, so let's say that this is the glove of the astronaut. There you go. That's his hand. That's the astronaut's hand right over here. And let's say he finds some piece of equipment on his, or she finds some piece of equipment on them that they can throw. They can take off of their tool set, and they could find the most massive object that they can throw. So what's going to happen is, for some period of time, while they push this object away, they will be exerting a force on that object. They will be exerting a force on that object for some period of time while they have contact with the object. And that entire time, that object, while it is accelerating, while the astronaut is exerting a force on it, will be exerting an equal and opposite force on the hand of the astronaut, or on the astronaut itself. So the object will accelerate in that direction, and while the astronaut is pushing, the astronaut will accelerate in this direction. So what you do is you throw in the opposite direction, and that'll allow the astronaut to accelerate towards the space shuttle and hopefully grab onto something.
And here's another link to a video that I think will help you understand all three of Newton's laws of motion. That's the end of presentation number 6 on Newton's laws. The next presentation number 7, will be on the continuity principle.
While studying kinematics, we saw that we could use math to predict the motion of an object. We could figure out where it has been in the past, where it will be in the future, how long it took to get there, and even how fast it was traveling. What we were really doing was analyzing how an object was moving. But why was it moving in the first place? In other words, what is it that causes an object to speed up? The answer is surprisingly simple. The only thing that can cause an object to accelerate is a force. In this video, we'll look at how forces influence the motion of different objects, and we'll challenge our intuition of how things work in the physical world. Here is a wooden apple resting on a countertop. Before seeing anything else, you've probably made a number of assumptions. We rightly think that the marble counter is heavy and rough, and that the apple is smooth and light. Say we plan on giving the apple a shove to the right. We all have an idea of how the apple will slide and stop. And thanks to our intuition, we can make predictions like this on a moment-to-moment basis without much effort at all. But what if it were possible to remove everything that our intuition is based on? What if we could remove all the air in the room, which can cause air resistance? Remove all the friction from the ground and walls, and remove the force of gravity? Now if we pick the apple up and let it go, it won't move anywhere because there's absolutely no forces acting on it. If we bump the apple now, would it ever stop moving? The truth is, once we give the apple a bit of velocity, it stays at that velocity, moving in a straight line until it's bumped again. This isn't just an imaginary experiment. It turns out that this is exactly what happens in outer space. But before we go any further, let's look at a little history. The first person to make this claim lived over 300 years ago. His name was Sir Isaac Newton, and he was a brilliant scientist, brave enough to challenge our intuition about everyday physics. Newton's goal was to figure out how the world around him worked. He had the thought that everything we see follows a few simple rules, which when added together, build up to explain the complicated physical interactions all around us. Newton's predictions are now known worldwide as Newton's 3 laws of motion and are used when dealing with anything that moves, from cars and trains here on Earth to spaceships that fly to the moon. At the start of the video, we asked the question, what causes an object to speed up? Newton answers this question in his first law of motion. An object with constant position or constant velocity will remain at that position or velocity unless acted upon by a net external force. Well, this is just reiterating what we already realized. The only thing that could cause our apple to accelerate was a force. So what is the next logical step in understanding why things move? If we now know that a force causes acceleration, we might also wonder how much acceleration we can get from a certain force. The answer to this is actually Newton's second law of motion. F is equal to m multiplied by a. This means that if you want to speed up an object by a certain amount, you will have to adjust your force depending on the mass of the object. Heavier objects need stronger forces. Let's look at what this math means in real life. There are 3 variables in the equation, so we'll look at 3 examples, each with one variable held constant. But before we start, let's bring back gravity. Okay, first let's hold the mass constant. Let's bring in 2 toy blocks of the same size. This part is pretty intuitive. If we gently push the first block it'll accelerate slowly. But if we push the second block with twice the force, it's going to accelerate twice as fast. What if we were trying to push something much heavier, like two large masses? Now our robotic arm has to push at 100% of its strength to move these objects. And when we push the heaviest mass, it's a big struggle. But when we push the smaller heavy mass, even though we're pushing with the same force, we can make it move faster because it's lighter. In our third experiment, let's drop a hammer and a feather from the same height at the same time. What does your intuition tell you will happen? Most people imagine the hammer hitting the ground first, because it's heavier, so it falls faster. Let's try it out. They hit the ground at the exact same time. Amazingly, humans have actually done this experiment on the moon, and it turns out that our predictions are completely correct. Let's look a bit more at this third experiment, since its results are a bit unexpected. If the acceleration of the hammer and feather are the same, then what does that tell us about the forces and masses? Well, we know that the hammer has more mass than the feather. So that means that for the math to work out, the force of gravity on the hammer must be more than the force on the feather. So we know from Newton's second law that the hammer and the feather fall at the same speed, because even though the hammer is pulled with more force, it also has a greater mass. So in the end, the ratio of force to mass is the same for the two objects. This is why they fall at the same rate. What we have just stumbled upon is actually a very important distinction in science. The force of gravity acting on an object is known as its weight, which is not the same thing as the object's mass. You can think of mass as something that belongs to an object no matter where it is, whereas the weight of an object changes depending on the gravity of the planet that you happen to be on. In outer space, your weight would be 0 newtons. But since acceleration is constant at 9.8 meters per second squared on Earth's surface, we can use the force of gravity is equal to the mass times the acceleration of gravity to quickly find the weight of an object from its mass, or vice versa. For example, the weight of a 10 kilogram mass on Earth's surface is 10 kilograms multiplied by 9.8 meters per second squared, or 98 newtons. So now let's look back and try to explain why our intuition was wrong. What goes on when there is air resistance that makes the feather fall more slowly? Let's look at the feather on its own to start. We just found out that the feather has a small weight because it has a small mass. So this means that the force of gravity pulling on the feather is relatively small. So let's draw a small arrow to represent the force of gravity acting on the feather. What other forces are acting on the feather? Well, in a vacuum, gravity would be the only one. But with air resistance, there is actually a second force acting on the feather, in the opposite direction to the force of gravity. For a hammer and a feather, the force of air resistance is nearly equal. But since a hammer has such a larger mass, the hammer barely notices this small force of air resistance. For most calculations in high school physics, we deal with objects that are large and fairly heavy, so you can usually ignore air resistance. But for a feather, it makes all the difference. The analysis technique that we have just used is one that you will use all the time from now on. The use of arrows to represent all the known forces acting on a single object is called a free body diagram. For problem solving in physics involving forces, you will almost always start by drawing one of these. On that note, we are now completely ready to tackle Newton's third and final law. So far we have answered our two biggest questions. First, what causes an object to accelerate? And second, by how much does the object accelerate given a certain force? It might seem like we have asked the two most important questions, but Newton thought of one more question to answer, which most people might not have thought of. The first two laws are centered on an object that is accelerated by a force. But what is providing the force in the first place? Newton's third law is that there is no such thing as a lone force. All forces come in pairs. In technical language, for every action force, there is an equal and opposite reaction force. Let's look at some examples. When a robotic arm pushed on those masses as hard as it could, the masses were actually pushing back on the robotic arm with the same force. When the Earth pulled on the hammer as it was falling to our studio floor, the hammer was actually pulling back equally hard on the Earth. But since the Earth is so large, we don't notice the Earth accelerating towards the hammer. And as you sit in your chair pushing it down with your weight, it pushes back on you with an equal force. You wouldn't even be able to walk if Newton's third law weren't true. When your shoes push back on the ground pushes forward on your shoes, and this is the only reason you are able to walk forward. Okay, let's take a breather. We've now covered all 3 laws of motion, and there were probably a few things we covered that didn't immediately make sense. Let's look at a generic example involving forces, and use Newton's laws along the way just to solidify our understanding of everything so far.